We are visiting a volcanic crater in the Arizona desert to check our models of what radio communication coverage will be like on the moon. We want kilometers of coverage, so we will be walking for kilometers. I wanted to put my mountain bike in the back of the van, but it's a minivan carrying a crew of 3 and all of their experiments, instruments, and supplies for a 2-week excursion. Also, I wanted to emulate a standing posture, and my bike's transmission has exposed moving parts to keep clean. So the best I could do was stash a couple of electric unicycles into empty crevices. We were glad to have them. I have been riding one to work for over 2 years now. It's a comfortable, powered commute. I am not tired or sweaty when I arrive at the gate. And yet, I was still able to cut my own contribution to NASA's carbon emissions by about 1.5 tons. This is Ravi, my intern. Ravi hadn't ridden a bike in a while, but he was eager to learn more about this technology. Building reflexes doesn't happen in a day, but it does happen after a few days. We might be able to bring the cost of landing on the moon as low as $200,000 a pound. This device has the mass of about 3 gallons of water. This device has the mass of about 4 gallons of water. The complexity of this machine is so simple, it has only one moving part. With most vehicle designs, the driver or rider controls the tire speed, and we humans apply full throttle or we lock the brakes. For enjoyment or panic, we operate these controls at the edge of traction. Intriguingly, the rider of a self-balancer surrenders direct control to a loop that optimizes acceleration to balance the rider. This landscape is primitive and ecologically delicate. Any trace that we leave in the desert can endure for years or even reshape the landscape, so we intend to leave no trace. The vehicles do have limitations. My pedal heights are fixed at about 4 inches. Pedal height droops during a tilt turn, which enlarges turning radius and reduces ground clearance. My machines came with tires that are optimized for dry pavement. These tires lose traction in deep, loose, dry sand. These machines were so easy to take along and really expanded the area we could cover. Might they be useful to explorers on the moon? To try the idea, I'll wear a backpack that weighs 50 pounds.
What's in this thing anyway? I've got life support, thermal control, power, and 20 miles of surface mobility. This is 20 miles of transportation stripped down to bare essence. I'm here today at a planetary surface analog that NASA uses to exercise its mission concepts.
I'm donning a goose down insulating layer, a helmet.
This glove has 2 layers with wrist protection built into it. This is a snowboarding glove.
Bulky gloves are hard to work in. My knees are already stiffened by an ice skating knee pad. A Tyvek suit will preserve marks of any contacts that I make with the ground. And the 50-pound pack changes my mass, inertia, and center of gravity to approximate 300 pounds in 1/6 g.
There's no pockets in this thing.
So, here I am in a new environment after traveling 2 days, mostly sitting in a van. I haven't ridden either unicycle in 6 days. First, I need to retrain my balance and muscular reflexes for these conditions. I'm wearing bulky gear that is hard to move and work in, and I'm carrying weight. My center of gravity is higher, making me less stable, and I have more inertia. And I have some anxiety about falling down in front of the cameras. Before I go anywhere on the unicycle, I should run a few drills to accustom and adjust my reflexes for longer stopping distance, mounting and dismounting, and how much traction my tires have against this soil. And then I proceed into the unimproved terrain, heading across the flat plain toward the rocky outcrop, threading my way around the sagebrush and between the bigger rocks. I put 130 miles a month on my unicycles commuting to Johnson Space Center. This one is my daily driver, an in-motion V8F. I don't expect to climb the hill, just see how close I can ride. I went until the wheel slipped, and then I turned and came back. I'm going as slow as I need to and avoiding spills. In the beginning here, I am not fumbling with the camera or cell phone apps, just focused on experiencing the ride.
Go.
Now I want to try the smaller, lighter Bigode M10-3, a 10-inch diameter wheel weighing a mere 24 pounds. I definitely feel tense at first. This unit could stumble over small surface features concealed in the sage, but it is also highly maneuverable. So I'm looking carefully where I'm going. I'm going as slow as I need to. It actually feels really slow, like I could walk faster, yet the video shows that I do move efficiently and outperform walkers. This is a surface untouched by bulldozers. Water has cut a few troughs that are a challenge to cross. The moon wouldn't have those. The sage drags unevenly on my pedals and conceals hazards. The moon wouldn't have that either. As I approach the hill and the incline begins climbing, the surface composition changes to bigger, chunkier rocks set in the loose, deep sand. And the machine spins out. I can walk out of the spin. I'm riding slowly. Wheeled vehicles just don't work everywhere, at least not with these tires. Bear in mind, between a camera, protective equipment, and the wheel itself, I'm managing my own risk for thousands of dollars in personal gear. It's just not going to work. That's as close to the hill as I can get. I have two options. I can just leave the machine. I do have to say that it is easy to lose sight of if you walk very far. In rough terrain, it does not function as a landmark. Or I can portage. I found another sand pit. When a self-balancer is off of the ground and it isn't perfectly level, it will spin faster and faster trying to achieve balance. There's an awkward little silver safety button that I'm trying to press with my thumb, which will disengage the balancing behavior, but it's hard to do with the glove. In 1/6 gravity, this would be a 4-pound carry. So, now I'm carrying it a short distance. I also do this when I commute to Johnson. I carry a string backpack in my commuter backpack to run errands. We want to take back some rock samples for laboratory measurements. Can I do that in a spacesuit on a unicycle? I used the 16-inch wheel instead of the 10-inch wheel. I think mostly because it's more familiar. I am riding uphill into rocky terrain.
Jarvis, display bearing to next waypoint.
It would be pretty nice to have an informatics system in this suit. That was topsoil. Now I want to collect rock samples, so I go where the rocks are. For comfort, I lightened my pack to 40 pounds, and I omitted the down coat. I didn't take a camera along, it would be more to manage. I did have to cross a couple of water-cut features. But this isn't my first ride anymore. I'm feeling pretty comfortable, less tense, working less hard, moving faster, and accepting more challenges. Thus far, my suit is pristine. In some situations, these machines tunneled into the sand, but there were long stretches of distance that they covered easily. I collected a total of 7.5 pounds of soil and rock samples. The surface of the moon has been pulverized, pounded to dust by eons of asteroid impacts. The moon has no atmospheric or hydraulic weather to blow, settle, wash, or otherwise redistribute this loose material. The unicycle was challenged by loose regolith. Loose regolith also was correlated with missteps during Apollo.
Here we go again.
I suppose traction will be a generic problem no matter the technique of locomotion.
Not quite.
I have learned that balance is trained, not learned. Roller skating isn't skiing, but the process of retraining balance can be generalized. I'm just glad the moon has no mud, and no hazards concealed beneath long prairie grass. Beyond technical challenges are the regulatory challenges. Transportation technologies, like communication technologies, are regulated.
How are you today?
I'm good.
Unfortunately, you have to walk from here.
Okay.
And
I just wanted to try.
yeah, unfortunately not. It's still not the right thing to do.
Okay. Anybody ever tell you why?
Not really.
Focused safety rules do not embody cultural exclusions. Safety does not require handlebars and hood ornaments. NASA's Apollo program fueled spin-off technological innovations that have been commercialized and standardized. We don't have to reinvent these for Artemis. But the Apollo program culminated before the modern era of technology regulation. Johnson Space Center no longer allows the commuter vehicles of that age to drive through the gates. The Department of Transportation opened in 1967 to integrate railroad, highway, and aviation infrastructures. And the National Highway Transportation Safety Administration was formed in 1970 to reduce the rate of traffic fatalities in the United States. Today, incumbent interests and technologies have regulatorily protected exclusive allocations of resources. To facilitate commercial partnerships through the attractive long-term cost efficiency of using modern technologies in space, the Artemis program and the Extravehicular Activity and Human Surface Mobility program will need to engage locally and internationally with protected interests to find ways to share the commons with new technologies.